Yes.
Good evening to all the estimated participants and organizers of this AICTE sponsored ATAL Faculty Development Program. It is a pleasure to welcome you all to this technical session 8, which promises to dive deep into the innovation world of dental implant optimization using cutting edge technologies. Today, we all explore the topic topological design optimization of dental implant, which hold immense potential in advancing the field of dentistry and improving patient outcomes. The session will focus on how topological design techniques can be applied to enhance the functionality and efficiency of dental implant, creating a blend of engineering excellence and medical precision. To guide us through this exciting topic, we are honored to have with us Mr. Piyush Ukey, an expert and visionary in the domain of 3D printing and biomedical applications. Mr. Piyush Ukey is the founder and director of New OSA Medi Equipment Private Limited, a company incubated at Vishweshwarya National Institute of Technology and mentored by Venture Center Pune. He has an experience of over 10 years in 3D printing for biomedical applications and has made a significant contribution to additive manufacturing, product design, and biomedical engineering. He has conducted numerous workshops, seminars, and training programs across the India in reputed IIT, NIT, IIIT, and government institutions to educate and inspiring the youth about advanced technology like 3D printing and product designing. In addition to his extensive academic and professional achievement, Mr. Ukey is a beneficiary of the BIRAC Big Grant Award and an ATAL Innovation Mission Prime Fellow. He is deeply passionate about advancing the use of 3D printing in healthcare and delivering innovative solutions in the biomedical domain. We are privileged to have Mr. Ukey with us today, and I am confident that his expertise will enlighten us about the transformative impact of topological design optimization in dental implant technology. Let us welcome Mr. Piyush Ukey to take the stage and share his invaluable insight on this fascinating topic. Sir, over to you.
Yeah, thank you, sir, for the introduction. I'll share the screen first. Is it visible, sir?
Yes, sir.
Screen is visible. PPT is yet to come.
So today's topic is topological design optimization of dental implant. So what I'll try to do, like we have two approaches. Either I can go theoretically or I can go with the actual practical application, how exactly they're creating and manipulating the CAD models. So I'll try to go with the practical application perspective side, like how we can create, how we can manipulate the CAD geometry, and what kind of softwares are been using to develop these kind of models. So let's begin with the session. So first, let's talk about the different kind of modeling softwares which are available. If we talk about the biomodeling software, that is for conversion of CT scan into a 3D model. So we have two softwares. So first one is Materialize Mimics, and second one is 3D Systems DICOM to Print, which is D2P. And if we talk about the open source software for biomodeling, then we have 3D Slicer. And so these softwares are being used to convert the CT scan into a 3D model. So followed up, then we have the CAD modeling packages. In CAD modeling packages, we have CATIA, SolidWorks, Fusion 360, Creo. So these are also commercial software. And if you talk about the open source free software, then we have FreeCAD, OpenSCAD, and SketchUp. So these softwares are being used to create the CAD geometry. So the methodology will be, first of all, we will convert the CT scan into a 3D model. The patient-specific 3D model is going to be created. Then by using that patient-specific 3D model, we will generate an implant. So this implant generation can be done on any of the packages from any of the CAD packages. And lastly, like another approach is like sometimes the implant which we are trying to make, it has a very free form kind of a surface. Like when we are using this CAD, commercial CAD software, the mechanical CAD softwares. So these have the constraints. So we need to give them certain kind of dimensions, angle. We need to define the constraints. We need to define the sketch. Then only we can make the CAD model. But what if, like, if you talk about the skull? So does the skull have any kind of like, can we define the skull in any of the radius curvature value? We don't have any definite curvature value. Okay, like suppose if you want to make a sphere, so if we define the radius, then by using the radius we can define the sphere. But we cannot do the same thing by defining a particular digit. We cannot define make the entire skull model. So such kind of freeform models needs to be designed by using freeform software. So these form software are Blender, Mesh Mixer, and Mesh Labs. So these are the freeform software which we are going to use there. And once we made the entire geometry, like we got the anatomical model, we got the patient-specific implant, then we are going to print the model. So in order to print the model, we will be using either, like if you're going with the FDM kind of 3D printing technique, then we will be using Cura or Slicer. Or if we are printing it with the DLP technique, which is a liquid 3D printing technique, then we will go with the G2Box software. So these are the overall overview of the 3D modeling softwares which we are going to use to make any kind of a CAD model. So among the entire step, what I'll do, I have already got a 3D model from the CT scan of a mandible. So I'll be using that model with me because right now I don't have the license in the laptop to show you the software. Like we do have a license of D2P software. So we are using a DICOM to print software to convert the CT scan into a 3D model. But right now I cannot show you this process. So I have already converted the CT scan into a 3D model, and I'll be using the 3D model to do the further post processing to develop the surgical guides. Okay, and we will be using a mesh mixture software. Okay, so the outline will be like I'll give you the overview of mesh mixture software. Then where we are going to create and manipulate the CAD geometry, we will create a surgical guide. We will try to make the scaffolds and all this CAD model will be prepared on the mandible. Then we will export the model into a STL file, and then we will see how we can transfer this STL file into a 3D printing software, like the pre-processing of the software, the generation of G codes. So that thing we will take care in the third step. So this will be the step. So let's begin with the software. Yeah, sorry. So this is the mesh mixer software which has been developed by Autodesk. Autodesk have also developed the AutoCAD software, AutoCAD Fusion 360. Then we have Solid Edge software which has also been developed by AutoCAD. So these are some of the softwares which are developed by AutoCAD. And Mesh Mixture is an open source software which where we can freely sculpt the model. So it is more or less like we all know about the manual sculpting, like the clay sculpting, what we usually do to make the models, the sculpt models. So this is nothing but the same kind of technique, but here instead of going with the manual sculpting, we are going with the digital sculpting. So once we open the software, so this is the screen which we are going to see. So this is our main view window where we can where the CAD model or CAD geometry is going to be seen. So these are the toolbars and these are the action buttons, action view parts where we have different options or different functions which we are going to use to manipulate a CAD model. Okay. So if I click on the file, so here I can see all the different kind of features which are available in the software. Like I can open the predefined model, or I can import the model and do the manipulation of the model. And then we can, in the help, we will find out all the manuals and help which is been needed to manipulate a design. And in the feedback side, we can get the feedbacks. Okay. So the first step is to import the CAD model. Now, if while importing the CAD model, what kind of files are being supported? That is going to be the first question. So it supports obj, .pli, stl, amf, and 3mf kind of file structures. So all these type of file structures are being supported by the mesh mixture. So this is the mandible file which I have already created. So I'll import the STL of the mandible. Sorry. So we got the mandible STL file imported. Okay. Now I want to see the different kind of features which are available in the software. Okay. So if I click on the view button, again I'm seeing these are the different kind of options which are available. Suppose if I want to see the mesh of the model, so I'll just click on this show wireframe, or I'll press W, which is already been shown here, the shortcut W, or we can click on this button and it will show me the mesh. So this is the mesh of the model. If I want to see the boundaries of the overall boundary of the entire print zone, that can be seen from here. This is the grid, the central grid on which the model is usually been made. So this is the central plane of the software, and this is the printer bed. Okay. Suppose if I want to see where exactly my model is being placed in terms of the printer, so that printer bed can be like I can open up the printer bed and see where exactly the model is. Okay. Then we can translate and manipulate, reposition the model so that the model is being placed on the printer bed. And from this option, we can choose it supports almost all the open source 3D printers which are available in the market. So from here we just need to select the maker, the manufacturer company. Suppose if I'm using the FlashForge Creator Pro, so first I'll click on the FlashForge. Then inside the FlashForge it will show all the 3D printers which are available. I do have Creator Pro 3D printer with me, so I'll click on the 3D Creator Pro 3D printer, and it will show me the build volume of the 3D printer. So this rectangular box which we are seeing here, the wireframe model which we are seeing here, is the print volume, is the printer print volume. So suppose if I have a model which is far bigger than this, so suppose I have a model which is far bigger than the print volume, then I can judge whether the model is going to be printed as a single part or not. If some certain kind of bigger parts are there, then we need to cut the part into different pieces. We will print the part into the different pieces, and finally we will assemble the part. The glue assembly can be done by either gluing or screwing or any other kind of joining techniques. Okay. So this is the overall structure, like the printer, the view port, how we are going to see. And if you talk about the options, on the left hand side, we have a different options. So the first one is the import. Again, in the import, it will ask me what kind of file I need to import. Okay. So for ease of doing the design, I'll first hide the printer and the grid. So I'll again go to the view. I'll hide the printer bed and I'll hide the grid. Sorry. And I am also pressing the W button. I don't want to see this wireframes, the mesh. Okay. So the first option is the import. From import, we can import the CAD model. Then we have mesh mix. In the mesh mix, we have different kind of primitives which are already been developed here. We just need to call different primitives. If we need to use those kind of primitives, so we just need to call this primitive, and we can do our CAD manipulation kind of thing. Okay. Then on the first side, then we have the primitive. In the primitive, we have a different kind of, again we have different model, like arm is there, ears are there, heads are there, legs, letters, miscellaneous number. So these are different kind of model which are already there in the library, which we can use to manipulate the part. Suppose if suppose I need to add an ear on this mandible. So what I'll do, I'll click on the primitive. I'll just do the left click on the ear. I'll do left click on the ear. So these are all the different type of ear which are available in the library. I'll click on this. I'll keep the left key pressed. I'll drag the model onto the viewport, onto the action design area, and I'll press the left key. I'll remove my left key. So the model will be placed within the window. Okay, I just need to press the accept button. So here we can see the model has been imported into the file. Okay. Now suppose, so this is how we are going to import the model. Another option is the select button. From the select button, I'll delete this here. Okay. So the second option is the select. So from the select, we can select the triangle or the surface which we need to modify it. So the orange one is a selected surface. And now I am pressing W to see the wireframe. So we can see the mesh which has been selected. Now suppose, okay, I'm just doing the left click on select and selecting the area. As soon as I select the area, this new window will be popped up. So this window will have a different kind of options which we can do with the select toolbar. Okay, first in the edit, if I go in the edit, I can see erase and fill. It will erase the surface and fill it with a recreate a gap with a new surface, or discard, reduce. I can this remesh it. If I want to reduce the mesh size, I can do that with the reduce, or from remesh, we can remesh the mesh. And these are the different type of meshing options which are available there. So we are remeshing it, then extrude. Suppose I want to extrude the model, so I can extrude it. Then extract. If I want to extract this surface, the selected one, I can do that. Offsetting. Offsetting again, adding a thickness onto the selected part. Bridge, join, and these are other options which are available. Okay. Then we have modify. In the modify, what we can do, we can, if I want to have a smoother kind of boundary, here we can see very rough selection is there. If I want to have a very smooth selection, so I'll click on the modify, I'll click on the smooth boundary and accept. Now we can see a smooth curvature has been selected. Okay. So these are the options which are available with the select. Then in the sculpt, we have different sculpting options. Like suppose I want to add something, I want to give thickness. Like I think this bone, suppose this bone is quite thin, and I need to add thickness on this bone. So I'll first I'll go on the brushes. These are the different kind of brushes which we can use to resculpt the model. So this is draw, flatten the surface, inflate, pinch, move, spikes, bubble smooth, again smooth, shrink smooth, and these are the robo smooth. So if I want to add, like suppose if I want to add certain material on this depressed kind of area, so I'll go on the brush, I'll click on the draw, and I'm adding the surface. Can you see the thickness has been added? Okay. So from here we can adjust the strength and the brush size. The higher the strength, the more material is going to be added. The faster the material is going to be added. And this is the brush size. Okay, I'm pressing Control Z. Likewise, if I want to flatten something, like I don't want this curvature, so I can flatten the thing. Then if I want to have a smooth curvature, I'll select shrink smooth. Suppose these are the spikes which are there. I don't want this kind of spikes. So I want a smooth surface. So I'll click here. I'll click on the shrink smooth, and I'll click on the smoothen surface. Can you see the surface is being smooth? So likewise, we can make the surface smooth. If I want to move something, like if I feel this condyle region shouldn't be here, it has to be moved somewhere. So again, I'll just select, I'll increase my brush size, I'll select this and I'll move it. Okay. The pinch one will create a fine line here. So it pinches and creates a fine line. Okay. So these are all the options which are available in the sculpt side. Now, if I want to translate, okay, I'll do one thing. We will use this head. Suppose uh, I want this mandible to be inserted here in the lower jaw portion. So what we can do? So first of all, the orientation is not okay. Okay, we can see here both the models are at different orientation. So the first thing is we need to do the proper orientation of the model. So in order to do the proper orientation of the model, I'll left click on the mandible, then I'll click on the edit. In the edit, we can see the transform option. So from the transform option, we can actually transform the model. If I want to rotate the model, if I want to move forward and backward the model in any axis, that is possible with the transform. Basically, the translating option. And third one is the rescaling. So here I can see in this option we have either uniform rescale or we can do the manual rescale. If I have clicked on the uniform rescale, so this is size X, Y, and Z, and it is giving me the dimension in X, Y, and Z. I want as 130 mm in X direction. As soon as I pressed enter, the Y and Z value will be automatically calculated. Why? Because we have selected the uniform scaling option. Okay. Suppose instead of uniform scaling option, if I untick the uniform scaling option, now I can rescale it in every axis based on the values which I want to be inserted there. Suppose I want 130 mm in X, I want 115 in Y, enter, and I want 100 mm, 110 mm in Z. Okay, and then accept. So now I can manipulate the CAD model as per my scaling factors. Or if you want to go with the uniform one again, then we will enable this uniform scaling option and change this value. Now instead of 130, if I want to go with 150, so you can see the Y and Z have automatically been calculated. Okay. Another option is here we can see certain kind of the square blocks are there. Okay, each and every color represent one axis. So this green color is representing X, sorry, Z. This is Y, sorry. So this is Z, this is Y, and the red one is X. Okay, and this block, uh, the cubical block, the square blocks, it represent the scaling in that particular axis. So now suppose if I want to scale in only in Y direction, if I left click on this square and move my mouse, so it will rescale only in one direction. The same thing will be in another direction as well as on this direction. Now, if I want to do uniform scaling, so here we can see a small cube. If I do left click on the small cube and move my mouse, it will rescale it. Okay. So likewise, we need to rescale the model. So we can rescale the model. Now I want this jaw to be inserted onto the face. So what I'll do, I'll again click on the edit, transform. Okay, I'll do the top view. Now I'm moving the axis, rotating it. Again changing the view plane, rotating it. Now translating. Okay. Sorry. Now inserting the jaw into the face model. Now we can see here, as soon as I have accepted, I have repositioned the jaw. But now we can see the jaw is somewhat bigger than the face. So we again need to rescale it so that the jaw can be perfectly fitted into the face. So to rescale it, I'll again click on Edit, Transform, and I'll use this cube to rescale it. Okay, it is perfectly inserted inside the model, and now accept. So we have what we did. We have inserted the skull into the face model. So this is how the transformation has been done. You will understand why we need, why we are using this when we will define the surgical guides. Okay. Then we have analysis. In the analysis, we have inspector. If we do the auto repair, it will automatically repair the CAD model. If you want to check the thickness of the model, then we have this thickness option. As soon as I click on the thickness option, it will ask me what is the minimum thickness which needs to be checked and what is the minimum defect size which needs to be checked, and it will automatically check the model. Since this is a thick model and it doesn't have anything which is less than 1 mm, that's why it is not showing here. So I'll show you that. I'll first click on view, object browser. As soon as I click on the object browser, it will show me all the components which are there into the design plane. So we have the face, we have the mandible. Now I'll hide the face and let's do the analysis on the mandible. So again, analysis and done. Oh, sorry. So can you see here the red zone? The whatever the red zone has been shown here, it has a thickness less than 1 mm. So it will, as we get the colorful image in FE analysis, likewise the same kind of image here we are going to get in the analysis thing, where it shows which is the minimum wall, where is the minimum wall. So and we can add the thickness on the wall if it has been needed. Okay. So this is how we can analyze the model. Now let's begin with our original task. So this is the overall overview of the software what I have tried to give it to you. Now let's begin with the task. Our first task, that is to make the surgical guide. Okay. So I'll delete this model. So to delete the we have two options. Either I can select the model and delete it, or I have just undo it. Undo it. Or I can import a fresh model. When I'm importing a fresh model, it is asking me to append or replace. If I'm doing append, so it will keep the original two models here itself and it will call the third model. If I'm doing the replace, so it will replace the entire models which are already there in the library. Okay. Here you can see in this library, the old models are been replaced. Now again, I'm doing the import, append, and suppose I'm calling this another model. Can you see this model has been imported here? So this is what is happening in Apex append. Okay. Now we got this CAD, this mandible ready here. Now our another task is to make a surgical guide. Suppose if you want to make a surgical guide, and these are like in a previous session we have discussed about the pre-surgical planning kind of model, where we can make the surgical guides, the jigs and the jigs, which we can use, which we can place on the model on the patient itself, and it will give us a proper kind of curvature on which the implant needs to be inserted. So this kind of, if you want to make such kind of surgical guides, then what is the procedure? So the first thing is we have two approaches. So I'll, tell you both the approach. to begin with the first approach, what we can do is like I'll first select the model. I'll select the tool on which the guide needs to be prepared. So suppose these are the three tools, three tooth on which the guide needs to be prepared. Okay. Now I want a smoother kind of selection. So to have a smoother selection, I'll click on modify, smooth boundary, accept. So we got the selected model. Now I want this tooth as a separate kind of model. I don't want it to be a part of a mandible. So again, I'll click on the edit, separate. Now here in this object browser, can you see like we instead of having one component, now we have two components. So this is the first original mandible and this is the separate selected tooths. If I hide the first one, I can see the second model. Okay. And this is the original mandible. So on this mandible now, our next task is to repair the surface. Here we can see the pink surface. So this pink surface is nothing but the inside edge of a STL. How we can define how we can identify whether the surface is outside or inside of an STL? It usually depends on the normal of the triangle. Like every STL has a STL is nothing but the surface approximation of a surface approximation into a triangular surface. So on suppose this is a triangular face what we have. So on this triangular face, the facet normal is going outward. So that area will be shown as a green color, and the inside of the surface will be shown as a pinkish color, so which is the inside surface. So now I just need to fill up this surface. So I'll click on the analysis, inspector, auto repair, and then so here we can see. So we got the closed surface, the closed model, and this is the original mandible. Okay. Now it has some kind of defect. So what I'll do, I'll again call the fresh mandible. So I'll click on import, append, and mandible demo. Okay. Now we have again called the original mandible here. Now we can see both the models are overlapping each other. Now we want this greener tooth as a cap on the actual mandible. So we need to place this tooth as a cap on the mandible. So for that, what I'll do, we need to have certain kind of thickness on this cap. So first of all, we need to generate a thickness on the model. So in order to generate thickness, so we just need to do double click on the model. The entire model will be selected. Then go to edit, offset, and add the thickness. Now suppose if you want, we want that the guide thickness should be 2 mm. So I'll set the offset distance as 2 mm and accept. Got it? And this is the original mandible. Here can we see the thickness has been added on the cap. Now, does our cap have any kind of cavity? Like suppose if you want to place this cap onto the mandible model, can we place it? No, we cannot place it right now because this is a solid cap. It doesn't have any kind of cavity on the model. So first of all, we need to prepare a cavity. We should have certain kind of impression, the negative cavity on this cap so that it has a perfect fit on the model. So in order to create a cavity, what I'll do, I'll open up the mandible. Now we just need to click on the model. So this is the first model on which we need a cavity of the mandible. So by pressing Control key, we just need to select both the models, the first one and the second one, and then this new pop-up window will appear. So in this new pop-up window, we just need to click on the Boolean difference. As soon as we click on the Boolean difference, I'll accept it. Yeah. Now can you see the cavity has been created? Now this will be a perfect fit on the mandible. So again, I'll import, append, and I'll call the mandible. See, now can you see it has a perfect fit on the model. Now the cap has been perfectly fit. Now we got uh, the fixture ready with us. Okay, the surgical guide is ready, but still it doesn't have any kind of this don't have any kind of access the opening through which the screw is going to be inserted. So for that we need a dummy implant. So in order to call a dummy implant, what I'll do, I'll again click on the mesh. I'll click on the mesh mix, primitives, and this cylinder. Now suppose this is a dummy implant which we need to insert into the mandible. So what I'll do, I'll click on the edit, transform, and we just need to place the implant onto the model. Okay. And if I just hide this model, I can see where exactly the implant has been inserted, at what axis, at what position the implant has been inserted, whether it is damaging any nerve, whether it is pressing any nerve or not, or it is going to any critical area. So all those things can be visualized. So this is how we do the virtual surgical planning. So in virtual surgical planning, we can place the implants, the plate onto the actual bony model, the patient specific bony model, and see the fitment and see the actual trials there itself. So from here, let's assume that we have placed it perfectly onto the model. So this is the first implant. Again, I'm just duplicating the implant here by pressing this key. Okay, I'll click on the edit, transform. I have rotated this implant and I'm placing the second implant on this in vertical position and accept. Okay, so now we got two implants which needs to be inserted there, and we got the axis. Now another step is we need the cavity onto the guide by which this implant is going to be passed. So to create a cavity, so first thing is I'll hide all the models. I'll just bring this implants here. I'll do the control. I'll click control and select both the models. Then I'll combine the models. Now instead of having two different kind of component, I'll have only one component. Okay. So this is the single component what we have, and this is the cap. Now in this cap, we need the impression of the implant. I have created a copy of an implant. Okay. So first of all, again the same procedure. I'll press the control key. I'll select the main body, then the separate differentiating body, and I'll press Boolean difference. And then we got the cavity here. The cavity has been prepared here. Okay. Now we need to check whether it is a perfect fit or not. Again, we will call the actual mandible here, and we can see the surgical guide has been properly made. Okay. So this is how the surgical guides are actually made in the uh, are actually being made. Now we need to export this surgical guide. So to export the surgical guide, I'll click on the file, export. So I'm saving it as surgical guide demo model. Okay, so we have saved the model. So now I'm just deleting this surgical guide. and I'm sorry. Yeah. So here now you can see. So this is the actual mandible, which on which the cap or the surgical guide has been placed, and this is how the implant will be passed, screwed. Okay. So this will be the actual procedure at the time of a surgery. So they will first place the cap here, the guide here, then they will do the screwing process of the implant. So now I am deleting this thing. Hmm. So this is the CAD model what we got. Sorry, this is the actual mandible what we have. Now next task is, now we need to do the scaffolding. Suppose if you want to prepare a scaffold. So how we can prepare a scaffold? Now, in order to prepare a scaffold, first of all, we need to create. Let's create a certain kind of defect here. So to create a defect, what I'll do, I'll just call this model somewhere here. Now, instead of selecting the Boolean difference, I have selected a Boolean intersection. So what it will do, it will only highlight the intersecting geometry between the two components. So it has highlighted the intersected geometry. So this is just a example, like we're trying to create a defect here. So I'll export this as defect. I'm just adding a thickness of 0.5 mm and creating a defect here. Okay, selecting and adding thickness. And now first I have again press control and I'm selecting these two objects. Now we have three commands here. First is union. If I press on the union, so it will add both the geometries as a single component. If I, instead of going, if I click on the difference, it will create the cavity there. So it is asking us to smooth this edges. Now here we can see the cavity has been created. Suppose this is a dummy cavity. So now we need to replace this cavity with the scaffold so that the bone can be regenerated there. So to make that thing, so we have already prepared this defect model here. So suppose this is the suppose this is the defect what we got. So in this defect, I have placed this scaffold. Now I need to replace the defect with the scaffold kind of bone structure. So the first thing is we will first prepare the structure here. That in this structure, then I'll open up the mesh. We need to remesh the entire structure. So again to remesh, select the entire thing, then do the remesh. And we need a coarse mesh here. So this is the coarse mesh what we got. Then I'll click on the edit. In the edit, we have a make pattern option. Then we will click on the make pattern. And from the make pattern, so these are the different types of pattern what we can have. So from here, I'll choose the lattice structure. Then we can select the element size, how much is the element height, how much should be the element spacing. Suppose if I want to control the diameter of the element, so this thing can be controlled from here. As I'm changing the values, you can see the cylinder, the size of the cylinder has been getting changed. And from here, we can change the space. Like if you want to have a highly dense kind of model, if you want to have lesser density model, so this densities can be changed from this element spacing. So once we have highlighted all the values, we just need to add. So it will automatically convert the entire model into a scaffold model. So this is the scaffold model what we got, which has been placed on the mandible model. So now we will print the scaffold with the bone biodegradable material, which is hydroxyapatite or any other bony material. And then we will place this model onto the actual patient. We will implant this scaffold into the patient and allow the bone to grow on this scaffold. So this scaffold can be made in two types, like either we can use biodegradable kind of material. If we're using biodegradable material, slowly the scaffold will get degraded and the fresh bone will replace the gaps which has been degraded. Or we can use this scaffold as a permanent kind of scaffold. So whatever the remaining gap is there, in that remaining gap, the bone will regrow. So this is how we can generate the model. So we understood how to make the surgical guide and how to design the scaffold. Now, if you want to print this scaffold, so when I'm saving this scaffold as export and scaffold. Now our designing task is fixed. Another task is to get this part printed. So to get this part printed, we will be using FDM kind of technique. And in FDM kind of technique, we are using the Cura software. So this is the basic interface of the Cura software on the right hand side. As I click on the standard quality, all the settings, the print settings will appear here. So here we have a different kind of settings which we can use to print the model, like the quality, where we can change the infill type, the infill thickness, the layer thickness. Then we have the shell. In the shell, we usually define the number of contours which needs to be printed there. Then we have infill, where we can control the density of the part. Then material, print speed, travel speed, cooling, whether we want the cooling fan on or off, support structure, build plate adhesion, how the part is going to adhere the build. So for that, we have different options, like we have brim, we have skirt, we have raft. So these are the different kind of option what we have in the build plate adhesion. Then if our system is has dual kind of nozzle, then we have this dual extrusion setup, or else this setup will be this option will be disabled. So these are all the options which we will be used to get the part printed to generate the G code. So again, here the same task. First, we will import a STL file. So to import a STL file, I'll press File, New Project. I'll click on this. And I'll bring in the scaffold and the surgical guide. Okay. So here we called these two parts which needs to be printed. So this is the build volume of the entire printer. And the build volume, we can see where exactly the part is been placed. So if we want to reset the orientation, so we can just we can do the left click of the part and we can place the part anywhere under the platform. If you want to change the angle, the orientation, then we just need to click on this rotate button and we will rotate the part. We will rotate the part as per the need, like what exactly is the need, how we are going to print the part. We will select the best possible orientation based on the surface finish here. So suppose this is the orientation what we have selected, because we want the inner surface, the inside surface to be smooth. That's why we have selected this kind of orientation. So whatever the support will be generated, it will be generated on this top surface. And wherever the support is being generated, that surface is usually been rough. So if we are printing it with this orientation, then the support will be generated on the inside surface, and this inside surface will become rough. So we don't want that. That's why we are changing the orientation. We're changing it like this. Okay. And again, the scaffold, like we want to print the scaffold as it is on the same orientation. So we have placed the part onto the bed platform where needs to be printed. Now we will select the print parameter. First of all, on the quality, from the quality, I need to choose the layer height. Suppose I want to get the part printed with a layer height of 0.15 mm. I have selected that. Then infill, I want the part to be printed with 100% infill. Material is, then in the material, we will change the print temperature. Suppose we are printing it with ABS. So ABS usually prints with 210 to 230 degrees Celsius, or in the sometimes to 40 degrees Celsius. So it depends on the grade of the ABS what we're using. So suppose if I'm using a lower grade ABS, so I'll be printing it with 230 degrees Celsius. And again, the build platform, the temperature of the build platform is 95. It ranges from 90 to 110 degrees Celsius depending on the type of a grade of a ABS that you're using. Then print speed. For ABS, the print speed should vary from 50 to 70. To get a better quality of print, we are printing it at a lower speed for 50 mm per second. Then cooling, we don't want the cooling fan to be on during printing of a ABS material. Support, yes, we do need support structure. So I'll just enable this generate support structure. Build plate adhesion, we need the brim. Okay, so now we have selected all the parameters which needs to be there while printing the part. So I just need to click on the slice button. So here we can see the preview, the print preview. In the print preview, we can see how the part is going to be printed and how support structure will be generated there. Okay. If you want to see the nozzle movement of the nozzle, I'll just press play on this button. It will show me how the layer has been printed. And it has a 144 layers. It has total 144 layers. Suppose if you want to check the print preview of 55th layer, how this layer will be printed. So I'll again press on the play button and it will show how the part is going to be printed. Okay, so this is how the layer will be printed. Now, next task is to save the file onto the USB. So for that, I'll just click on the save file to. I'll select it on the USB as a demo. Demo G code. And now G code is ready to get ready for the printing. So we just need to use this USB with the printer to get the part printed. So I'll just take out the USB from the system, insert it into the 3D printer, select the file which we have just generated, and start the print. So that's how the print will start. So this is the entire workflow, how we can generate the model. So I have just tried to give you a small glimpse of what kind of models, what will be the methodology, what will be the process to make such kind of models. So this is how it works. Yeah. So any questions? So now I open the forum for the discussion. Like I have tried to show you the exact glimpse what the process is. And if you want to know anything else apart from this, just you can ask me.
Muthu Kumar is asking that any tutorial for this work is available.
Muthu Kumar sir, like you can find such kind of tutorials on YouTube. There are many tutorials on the YouTube, but if you want to go through the process, you can contact me as well. So I can walk you through the process, because on the YouTube, like very few tutorials are available where the process of converting the CT scan into a 3D model is been properly explained. And later on, the remaining process, you just need to learn each and every software individually, then apply the knowledge of converting the models, apply the knowledge for converting the models.
Okay. Another question by Mr. Venkatesh Naidu. If this part is intended for functional use, have stress concentration areas been identified and reinforced where necessary?
Uh, if you want to check the stress concentration area, then we need to do the FE analysis on the part. So by using the FE analysis, we can know the weaker side, where exactly is the weaker side, and then we can add a certain kind of reinforcement if needed. So in this software, we usually analyze the part based on the constraints of the 3D printing softwares. Like suppose if you talk about the suppose if you are printing with FDM kind of thing. So in FDM, the minimum wall thickness is 1 mm. So for that 1 mm, we can check if certain area lies within the 1 mm dimension or not. So those kind of thickness analysis is possible in mesh mixture. But if you want to go with the stress analysis, then definitely you need to use the FEA softwares.
Sir, another question by Kumar. How to do topology optimization of implant?
So for topology optimization, again the same thing, how we define the scaffold now. So based on the same kind of approaches, we need to do the topology optimization of the implant. So it's an entire bigger kind of picture what I have tried to show you in 1 hour of thing, because I have tried to show you how to manipulate a CAD model. So suppose like we have removed the tumorous part from the bone. So likewise, we just need to remove a certain kind of parts from the implant. We need to add certain thing on the implant, and that's how we do the topology optimization. But it follows the same process what we have tried to do. So instead of going with the implant, I have tried to show you the same process with the scaffold.
Another
Uh,
question by Praveen Dhandore. For simulation and analysis purpose, which configuration laptop should I purchase?
for that, either you should go with i5 or i7. i7 is preferable, which has a configuration like which has a graphics card of 4 GB with the latest graphics card of 4 GB. Now the GTX series which is going on. So that is more comfortable. But if your budget doesn't allow that, then definitely you can go with the i5 as well. i5 with 4 GB graphics card is a good combination to do the analysis, the basic analysis. But if you're working with a very high-end analysis, then definitely you need to go with the i7 processor.
Okay. One question from Mr. Rupesh Kharve. Such things are needed to be printed with 100% infill in FDM or less also will do.
Um, it the percentage of infill depends on the strength of the model, what is been needed into the functional part. Suppose like what we have printed is scaffold and the surgical guide. The surgical guide itself has a thickness of 2 mm. So in that 2 mm, we cannot print it with a less infill. Even if we try to print it with a less infill, it will create a kind of porosity there within the model. So it's better to print with 100% infill. But if you have any bigger kind of model, so you can optimize the infill percentage based on the strength requirement.
Okay. Another question by Mr. Venkatesh Naidu. Have areas requiring supports being analyzed for accessibility during post processing and potential impact on surface quality?
Yeah, like the major problem with the support structure is the quality, is the surface quality. Like why we changed to orientation for the surgical guide to be printed, because whatever the surface, the supporting structure which is binded here on the surface, like the support will touch the actual part on this surface. So this surface will be a slightly rougher surface. So that challenge is there. So wherever the support structure has been generated, it will access the it will have a very bad surface quality. So we need to do certain kind of post processing there to smoothen the surface. So usually, if if you know that you have a certain kind of, if you know a certain face of a model which you are printing is going to be there, which needs a higher surface finish, preferably that surface shouldn't be in contact with the supporting structure.
Then another question by Mr. Anil Vanalkar, sir. As you have
Mhm.
carried out FEA, I have one query. One day suddenly pain rises in my tooth, and on second day it breaks into piece and pain stops. So when pain rises means I think stress increases. So can we go to the on the root why this happens? Root cause why this happens.
So for that, so this is a biological kind of a question, because you need to first identify why exactly the pain is been causing. If it is causing by like if some kind of nerve is been pressing there, then definitely you cannot do the FE analysis there. But if it is due to the stress generation on the tooth, then that thing can be somewhat you can get the answer by doing the FE analysis. But still, this is something which is a tricky question. Like one day pain is there, another day is pain is not there. So from FE analysis, you cannot get the exact reason why, what is the root cause of the pain. If it is with the bony side, then you can know the weaker area. But if it is not with the bony side, it is due to any pressing of a nerve, then I don't know that. I don't think so that it can be known by FE analysis.
Then another question by Pratik Joshi. Any AI/ML based techniques are used in pre-processing of 3D printing component.
Yeah, the people are doing research on this area, the AI/ML. So they are using genetic algorithms to know the best optimum orientation on which the part needs to be printed. So they have the output as a quality of the part, the quality, the surface finish, the strength. So based on those output, the prediction model will give you the best optimum orientation as well as the process parameter, the values on which we are going to print the part. So it will give you those input parameters which we can feed and get the best quality of the part printed.
Right. Then one question from Rupesh Kharbe. Can we use Ultimaker Cura and 3D Slicer, which are open source softwares for commercial or PhD work or for actual implants?
You can definitely use for commercial and PhD work. Listen, what actually is happening now? If you talk about a 3D slicer, 3D slicer is basically been used to convert the CT scan into a 3D model. And when we are converting any CT scan into a 3D model, so we usually do certain kind of steps, like the software itself does the most of the thing. So we just need to select the optimum value on which the model will be converted from a CT scan into a 3D model. So if we are going with the paid version, the Mimics or the D2P, so there the level of accuracy is already been judged. So this software are US FDA approved. So by getting this approval, we know that whatever the data has been converted, it is properly been converted with certain level of accuracy. But if we talk about the 3D slicer, we don't have any information on the accuracy of the model which has been converted. So definitely then we need to rely on certain things to check the model reliability. So if we know that the model which you have converted is 100% reliable and 100% accurately converted, then you can use it for the commercial application. But if you are in doubt whether that model is been converted perfectly or not, then you cannot use it for the commercial application. I'll give you a classic example on this. Suppose I have a bone, like let's talk about a femur bone. if the femur bone has been converted there, and from the CT scan we can see the diameter of the femur bone is let's say around 25 mm. Okay, so when we have converted it by using Mimic software, that exactly 25 mm has been converted there. So the CAD model will have a diameter of 25 mm itself. But what if if we are doing it with the same process with a 3D slicer and it is converting it as 24.5 mm? We are not getting the exact diameter of the exact diameter which we are getting it on the CT scan. So this type of accuracy is missing in the 3D slicer. That's why most of the people, they don't rely on using the open source software for commercial application, but for the research purpose, of course, you can use that.
Then another question from Chiranjeevi Micharuppu. Is there any other software to support 3D printing, sir? I mean, converting codes.
You're talking about generating G codes, then yes, we do have like instead of going with the Cura, we can go with this slicer as well. And many manufacturer, they provide their own software. Like if you're using a FlashForge 3D printer, they have Flash Print software, which we will use to generate the G codes. So there are plenty of software. Some are open source, like Cura and Slicer. These are open source, and these two are configured with almost all the open source 3D printer software. But certain 3D printer manufacturer, they will provide you their own software. So you can opt with the Cura, or you can opt with the software which they have provided.
Okay. Other messages are for that you have nicely explained how to use mesh mixer software to develop surgical guide. Dr. Anil Sahu, Dr. R.S. Paude also highlighted the same very informative demonstration of use of mesh mixture and Cura software.
So Ankit is
Then
asking what are post-processing process after printing of surgical guides.
yes,
So yeah, for the post-processing, like if you're printing it with DLP 3D printing software, then you need to post-cure the material. The first step is support removal. Once the support has been removed, then if you're printed with DLP, the liquid 3D printing, then you will do the post-curing. Or if you're printing it with FDM, so we just need the support removal process, and then certain kind of surface finishing process if you need that thing. Like we can do the sanding, we can do polishing. So this kind of surface finishing operation can be performed. But apart from this too, we don't need anything else.
now I think so. Questions are over. So thank you so much
Yeah,
for the very nice session. Basically means explaining the work from software and that to online. How to work with that software is a very means difficult thing which you have taken it very easily and nicely, because people have enjoyed it and they are writing that you have nicely explained how to use the mesh mixer and Cura software for biomedical application.
yeah,
So
thank you,
thank
sir.
you so much, Piyush, and we hope that we will also uh, get benefited, because we have lot of work to do wherein we face difficulty. We will consult you for doing that work. Mr. Venkatesh Naidu, who has asked the question, is doing PhD under me, so
Okay,
he
yeah,
will be definitely in touch with you for
sure, sir.
his work, and whenever he faces the difficulty, because he is a little expert in mimics. He is working with mimics since last 2 3 years. So that's why basically whenever he face any difficulty, so he will contact you, right?
Sure, sir, sure.
So please
Because
help him. Right, right.
sure, no problem, sir. Because till date,
Yeah.
I have converted more than 150 plus models, the CT scan to 3D
Wow.
model.
Very, very,
So like
very nice.
uh, we have
So, so
we have a
you
very
are
vast
expert
experience.
into that.
Yeah.
Yes, yes. So,
So my
so
expertise is
that
mostly into the software designing thing. And
okay.
like even in this session, I tried to show you much more information. But the thing is, like the
Yeah.
entire process, designing process is a time consuming and it takes a
Yes.
very
Yes.
much time. Like
Yeah,
the
yeah.
1.5 hour itself is needed to just give you the overview of the 3D CT scan
Correct,
software, either the
correct, correct,
D2P
correct.
or the BIMX.
Yeah,
And
yeah.
later on, then switching from that software to the CAD model, then
Yes.
preform software mesh mixture for the another manipulating, then followed up with
Yeah,
the 3D
yeah.
printing. So itself, it's a very
Uh,
big task. So I try to concise
Correct.
it and and just give you the glimpse how the software can be used. If you want, I can show you some of the model what I have prepared.
Yeah.
I think the screen is already been shared, now.
Yes, yes, yes. Yes,
Yes.
it is being seen
Okay.
also. Correct.
Yeah. Okay. So this is one of the year model which we have converted. It looks
Okay.
like this is the finished one. So
Hmm.
here on this model, it seems like it is a perfect model, but it have taken a lot much of time to make the model.
Correct, correct, correct.
And
Yes.
this one is another model.
Yeah.
Yeah. So this is
Wow.
another model.
Skull.
So on
Yeah.
this,
Mm.
these are the artificial chicks. So the highlighted
Uh-huh.
area.
Yeah,
So
yeah,
these
yeah.
are the
Yes.
artificially made model. So like
Mm-hmm.
bringing on something external into the model and just
Right.
blending it
Mm-hmm.
with the original model. So we had only the mandible and the maxilla portion there. So we had to just
Yeah.
incorporate incorporate it with this kind of flat plates here on which certain kind of
Mm.
soft tissue will be incorporated. So this is
Okay.
this kind of manipulation needs to be there. And even like
Yeah.
here, we have defined the supporting structures. Like the opening of the
Correct.
mouth is fixed.
Mm-hmm.
This much mouth will be opened, and to open this much mouth, we have inserted this supporting structure here.
Correct.
So it also
Yeah.
gives the entire CAD model as a fixed opening as well as the support for the maxilla to withstand the pressure, whatever the pressure has been applied on the nose. So to withstand that pressure
Uh-huh.
and so that the model will not get collapsed. So that support is
Okay.
also been
Okay.
provided by the fillers. So such kind of
Yes. Yes,
manipulation
yes.
needs to be done a lot, and it takes a very bit of very much time to make this kind of model.
Yeah, yeah.
So
It's
this,
time consuming.
yeah.
And
So
that too, patience is also required. Time consuming is
yeah,
one part, but lot of patience is required because when I used to see now when Mr. Venkatesh works with that Mimic software, because this can be made in Mimics also, na? Basically. Uh,
Mimics will only give you the basic. Like if I talk about this software, this model.
hmm,
So the
yeah.
maxilla and the mandible, these two
Hmm,
models, I have got it from the D2P software from the CT scan
okay.
itself. And later on,
Uh-huh.
all these models, like the flat plate, the supporting structure, even
Hmm,
we can see these pegs are defined there to hold the soft tissue.
yeah. Uh-huh.
Sorry. So these all the models are created here itself in the mesh mixture. Then they are
Okay.
assembled all together, and then through Boolean
Hmm,
operation, like in the Boolean, we have applied the difference. So instead of
uh-huh.
sorry, so instead of applying the difference, we have used the union operation to combine all the part all together as a single model. Then
Okay.
this surface has been blended properly so that it doesn't
Oh,
appear
oh,
like something external is been added there.
yeah.
So to
Yes, yes,
blend the
yes.
surface again, the same thing, the sculpt and
Uh-huh.
smoothing the thing. So this is how we
Yes.
have just blended the surface.
Correct. Correct.
So
Yeah.
it is not like we are dependent only on one software. So we have to use
Correct.
multiple software to make the model.
Okay, so even mimics
Yes.
is not also means complete solution to the work.
No, Mimics is not a complete solution to the work. Mimics will give you
Okay.
the parcel solution, and you need
Uh-huh.
for the parcel solution you need to use some another software. Then later on you
Okay.
just need to integrate the solution all together to get the final output.
Okay. So how frequently you use mimics? Do you use mimics?
I usually don't use Mimics. I use the D2P software that I come to print.
Okay.
It is similar to the Mimic software, and
Okay.
it
Okay.
it doesn't have the tools as Mimics offers. It has a somewhat
Okay.
less tool what Mimics is offering,
Hmm.
but still it is
Huh.
good software to convert a CT scan into a 3D model. So
Okay.
for every case, I need to use that software. So my process
Huh.
is
Huh.
first I'll use the D2P. I'll load the CT
Huh.
scan there, get the initial
Okay.
CAD model of the anatomical model. Then I'll export the CAD
Huh.
model as an STL file. I'll import that CAD
Right.
model into mesh mixture for further
Huh. Huh.
manipulation. So in that process, whatever
Okay.
the post processing needs to be there, like many times
Hmm.
some
Hmm.
artificial debris are there or noises are there
Hmm.
which needs to be
Hmm.
deleted. So those
Hmm.
noise removal, surface smoothing process, or like
Right.
as we
Huh.
have, as suppose if we need to create a scaffold, or I
Hmm.
have created some pegs here or external surface here. So all these kind of
Hmm.
additional things will be created in the mesh mixture itself, and then they will
Okay.
all the model will be integrated finally, and then we will get a
Hmm.
final model. Sometimes mesh mixture,
Okay.
instead of going
Okay.
with the mesh mixture, we can go with the CAD modeling software as well. We can
Okay.
make
Huh.
the jigs and fixture on the CAD software like SolidWorks,
Huh.
CATIA,
Huh.
anywhere
Huh.
itself. We will call the
Okay.
model here, assemble it virtually
Huh.
in the mesh
Huh.
mixture, and then do the
Huh.
further integration.
Okay. Okay. That's great. So another question is there from Sudhir, which metal
Yes, sir.
additive manufacturing is suitable for orthopedic implants, DED or LPBF?
Uh, could you please elaborate what is DD and LPBF?
Uh, I
So, Dirji,
think
can you please
I
write full
will,
form of
I
DD?
will, or otherwise I will. Yeah, Sudhir has what kind of analysis we can do for implant? Another question is there. Uh, issue with the laptop configuration for the software.
Okay,
Venkatesh
okay.
is,
You're talking
I
about
have
the
attended
3D
your
printing software.
M&IT.
Yeah, Venkatesh, I
Yeah,
was there
if
in
I
the man
remember.
as well.
Right, right, right. M&IT Bhopal, I think so. Correct. Uh,
Correct.
correct.
So
There
I
is
think
some issue with the.
we have switched to this VN managed system then itself, where the software has been
Hmm,
demonstrated there.
right.
So, like you can use
Uh,
either DED or LP laser power bed fusion, any of the technique. So both techniques are suitable to make orthopedic implants. Uh, like orthopedic implant is not dependent on the process; it is dependent on the material. So basically, the implant have been made by using titanium TS6Al4B, the titanium alloys. So if your 3D
hmm,
printing printer is capable of printing that material, then of course you can use any of the technique.
correct.
And even
Yes.
like if, I don't know if you know the Mark Forged 3D printing company. Like there are certain FDM kind of printing techniques as well, which are there in the market, which prints the composites. So within the composites, we can make the entire model with the composite FDM kind of 3D printing. Then we will do the sintering. In the sintering process, the plastic will be vaporized. It will come out of the model, and only the metal part will remain there. And in the sintering process, then the remaining metal part will sinter all together, and we will get the final finished product. So that technique can also be used to make the orthopedic implants.
Okay. Thank you so much, Mr. Piyush, for
Thank you, sir.
elaborating and taking each and every question of the participant. Uh, we hope that it was informative to all participants, and uh, we will try to keep the mimics session also. We are planning to keep the some mimic session like you took for mesh mixer. So
Yes, sir.
just we plan to have that on Saturday. I will be asking my PhD student only, Mr. Venkatesh, to take that session for 1.5 hour. So that because we have 3 sessions on Saturday, so that they can get a feel of even Mimic software also. Yes.
Sure, sir.
Thank you. Thank you so much.
Yes, thank you. Thank you
Over
so
to
much, sir.
Nirvan sir. Yeah.
Thank you, Mr. Piyush Ukey, sir, for such an enlightening and thought-provoking session. Your expertise and in-depth explanation of how topological design optimization can revolutionize dental implant technology were truly inspiring. The examples and case studies you shared provided a clear understanding of the real-world application and future possibilities in this field. We conclude this technical session 8 on topological design optimization of the dental implant. On the behalf of the organization team, I extend my heartfelt gratitude to Mr. Piyush Ukey for sharing his knowledge and expertise with us today. Thank you, sir.